Okay, Andrew, how do you feel about getting started? Andrew's muted with his friends.
He's still trying to fix his Wi-Fi.
I wonder.
Larky, unmute yourself.
He's
Sorry
not even
for the
listening.
technical difficulty, folks. Yeah, who's streaming? Shrek in their background? Excellent. Excellent.
Nice.
Cinematic masterpiece.
Honestly, I'm not sure how long the video goes. I don't know if the whole thing got transferred or only a part, but it should be long enough that it doesn't matter.
Yeah, we can hear you now, Andrew.
Okay. I have successfully doubled my internet speed.
Thank God. I was really worried about your internet.
Oh, actually, I might have cut it in half. I don't know.
How networking works.
All right, cool.
Yeah, are you down to start, Andrew?
I'm ready. Yeah, that was a weird distraction. I apologize for that.
It's fine. Right. I think this is you.
Yeah. Okay. So we got everybody? Okay, so welcome to the beginning of our hybrid year, our semester, and the crash course for propulsion. So this is we're going to have 4 sessions. We're going to be running this over this week and next week. And the main goals here are specific engine hardware. And this is so that you can be prepared to start designing specific projects for our engine. And if not, you learn a lot about propulsion anyway, and it's a really good background to take into IREC or any other area. So our agenda, so today is mostly just an introduction. We cover what hybrid rocketry is, what sort of rockets this hybrid engine will go into, and the goals throughout the year, which involve like the testing and the eventual launch at the end of the year. And then over the next few days, we'll also talk about each of the components in our engine. We'll break it down by the concepts that make them necessary and how we designed them and how we got to that point. So we'll be able to take you through our entire engine and testing and everything that we do as a team and is necessary to know in propulsion. Yeah, so now we're ready to start day 1. I'm ready for the next slide. Actually, just the next one. So that's just our quick agenda for today. So we'll do an agenda review at the beginning of every day. So as a team, our objectives, like number 1 is most of the game engineering, the sorts of things you'd be doing in propulsion and in industry, and also just lots of all different types of industry skills and experiences. You get to meet a lot of cool friends and have fun. Additionally, as a team, our kind of like our hard goal is that we're designing, testing, and building a hybrid rocket engine that will go to 10,000, and it'll be in a rocket that's carrying a 4-kilogram payload. That's a good point, Justin. So please let me know if my audio is not going well. I'm trying to fix it, but so just let me know. We can figure this out. So yeah, so that's our technical goal. And our third goal, which is something I think we've done a really great job of, is just the general sharing of knowledge of rocket engines and rocket design work. And this is part of that goal. So some of the things we've done is just last month, we published a conference paper. And it was a research paper talking about the design of our engine, pretty similar to what we're talking about right now, actually. But this is really cool because we got to present at a conference with a lot of other like researchers, and we did a presentation right next to a team who was designing a hybrid rocket to take soil samples from Mars potentially back to Earth. So we got to that was a really cool experience for us. And another thing we have is we have a wiki page. So it's like an official illinois.edu wiki page. And we'll send it to you. We'll probably spam it to you like all the time. But it's a really great place to review things that we've done. So yeah, that's some of the things we've done to accomplish that part of the mission. Okay, so a bit of our history. So as a sub-team, a sub-tech project in ISS, we were started in 2013. None of us were around there at that time, of course. But they were working on kind of a proof of concept, just trying to see like whether they could get a hybrid rocket engine to work. And this was kind of one of their last hot fired videos before we kind of restarted this project. But this is hopefully our goal is to get something that looks like this on a much larger scale by the end of this year. So if somebody want to play that video now. Yeah, so like I said, so our current project was started right after that hot fire video was taken, that video of the burnt there. So once a previous team was able to prove that, we can make a proof of concept that can be done by university, like undergrad students, we started from scratch to make a large full-scale engine that's capable of launching a rocket, which is about 10 feet tall, in the IREC competition. So the IREC competition is a competition that will be going in this year, and it's called the Intercollegiate Rocket Engineering Competition. It's the largest amateur rocketry competition in the world. There are over 100 teams. I think last time there were 120.
Did we lose them?
Yeah, maybe let's
We
have
lost
everyone disable the video so that we
This
don't
project
stress
2
test
years
his
ago.
internet.
Am I still doing good on audio?
No.
No? Oh, that's okay.
You were out for a little bit, but you can keep going.
Okay. But basically, this is our third year in this iteration of the project. So in the 2018-2019, which was 2 years ago, we started the project, and pretty much all the members of our team who are still here all joined the project around this time. And it was really interesting because just like I suppose a lot of the new members who are joining now, we all came with no propulsion experience. Many of us were sophomores, so still early in our classes and stuff like that. But the first year we spent a lot of time learning about like what propulsion is and like what things we need to know and what's right and what's wrong. And it took us a while to really gain a pretty good understanding of that, which is one of the reasons we now spend so much time trying to like document the work we've done so that people in the future will have an easier time being able to jump right into it. And then over last year, so over the first year, we did a bunch of design, started to manufacture. We decided that to delay our entrance into IREC, ISS was still able to bring a team with a commercial engine, and they actually did really well. They came in 12th out of 120, and 6th in their specific category, so they did awesome there. And then last year, we continued the project and decided that we were able to look back and say we need about like 2 years to like super thoroughly design, test, and iterate on the engine. That way we can launch this coming June. We did a lot of great things. Like I said, we improved our design. We learned from some mistakes that we had after manufacturing hardware. And one of the big things we did was we matured our testing plan. We were able to start working with Purdue's Zucrow Propulsion Lab, which is the largest propulsion research lab in the US and possibly the country. I forget. It's really big. It's awesome because they're only 90 minutes away and they're super nice and super helpful. And then of course COVID hit and we got some big delays, but now we're here. We're back on track. We're lucky we gave ourselves 2 years because the COVID all the extra time was kind of taken up by COVID. So now we're back on a tighter schedule, but we should have enough time this year to finish up the last bits of design, finish up testing, and then launch in June. So that's where we're at. This is when you guys come in. So we've gotten a bunch of questions about this over the past few weeks, and this is just, I thought we'd start with this just because we're presenting a bunch of knowledge. So everything we've learned is mostly just from reading stuff online. So the two images in the upper left are the covers of two of our favorite textbooks, Rocket Propulsion Elements and Modern Engineering for Design of Liquid Propellant Rocket Engines. They're great references. They have a lot of information and they cover a lot. We have a picture of a few other of the papers that we use that cover injectors and also the fuels and propellants that we use. In the bottom right, we actually have our paper, which is now a published research paper, which can now be professionally referenced, which is pretty cool. Quick picture of our wiki, and also Sci-Hub, which is a really cool site, which if you put a link in there of a research paper from online that has a paywall, which is almost all of them, it'll allow you to see them. So we use it a lot. But most importantly, is just to Google things. It's really hard to just pick up a book and start reading it like a novel. Yeah, you can't read a textbook like a novel. It's too long. It's too hard. It's not fun. So the best way to learn is just when you have a question, Google it and learn as much as you can from that. And over time, the more questions you ask and get answered, the more you'll understand. And just because we're on Zoom, we're not in person, I wanted to make sure to show everyone's faces here. So here are people who have been like super involved on the team and helped publish this paper and also have been making this presentation. I guess we didn't really start with the full introduction, which we should have done. But I'm Andrew. I guess I don't have my video on right now, but I'm the one with the face over the word Andrew. I'm one of the co-leads this year, along with Zavar, who's further on the right. But everyone here is super knowledgeable, and if you ever get to see them, or I guess their name or whatever, feel free to ask anyone questions. We're all pretty friendly. But yeah, I think we'll continue from here. I'm going to show, now Zavar's going to start talking about actual propulsion stuff.
Hi guys, I'm Zavar. I'm the other co-lead besides Andrew. So before we get into hybrid engine rocketry, we're going to talk about the other two main types of rocketry, liquids and solids. So liquids consist of two liquid propellants, of fuel such as liquid hydrogen and an oxidizer such as liquid oxygen, which are mixed together and ignited. When most of you guys think about rocket engines, this is probably what you're thinking about. The Space Shuttle, Falcon 9, Saturn V, Starship, all use this type of engine. They all use this type of engine because it provides like a high level of control via valves and piping during the engine operation. They also have a high level of energy density and can generate a high amount of thrust. But they're also the most complex by far due to the amount of valves, pipes, pressures, and fluid dynamics involved. The other main type is solid rocket engines. These engines both have fuel and oxidizer mixed together in a solid propellant. They're the most simple because the propellant just has to be ignited and it goes. But once it starts going, you can't really stop it. They're generally undesirable if you want to do anything complex where you want to start or stop or throttle your engine down. But they're great if you just want to get off the ground, go real fast. They're also kind of simple to develop, and one of the reasons why we didn't really want to take part in them. And because that they're all solid, they're naturally very storable and pretty reliable. So now on to hybrids. Hybrids combine some of the features of liquids and solid engines, namely they use a liquid oxidizer and a solid fuel grain. They therefore have the same controllability as liquid engines, yet they're less complex due to simpler piping and have worse performance due to using the solid fuel. We like to describe them as well-rounded. They can be used safely, have an okay amount of thrust, and are a lot more interesting to develop than solid engines. In a hybrid engine, liquid oxidizer, nitrox in our case, is stored above the fuel grain in a high-pressure tank, separated by valves and piping. When the engine process is started, the valves are opened, allowing high pressure liquid to flow out and make contact with the fuel grain. This contact happens in the presence of an igniter, which starts the combustion process. This generates a lot of really hot gases, which exit the combustion chamber and into the nozzle, where they are expanded and generate thrust. This thrust is what's going to fly the IREC rocket. This was a really far simplification of everything, but over the next few days, we're going to go a lot more in depth on the details about this engine. Oh, and here's Avery to explain IREC.
Hello, everybody. My name is Avery. I have been involved in hybrid stuff since 2018, but I'm going to talk to you a bit more about the competition and rockets in general. And yes, the slides will be available. Oh, Zavar answered. I just have a quick question for everyone who's here. Do any of you, just put in the chat, have experience with rockets or rocket engines or anything like that? Few yeses. Theoretically. Oh, that's actually quite a few yeses. That's surprising. Yeah, I came into college with no experience of rockets at all. I didn't even realize that was like legal for students to do. I didn't even know. So when I came to college and found like hybrid and also rocket stuff, I thought it was the coolest thing ever. So I'm going to go over some of the basics for those of you who have no experience, because we don't expect you to have any knowledge at all. So ISS has attended IREC before. We went one time in 2019. And now we're planning to go again in 2021, which is very exciting. So when we went in 2019, we attended with a commercial motor. So Zavar mentioned solid motors. That is what we used at IREC in 2019. We just bought one. It's called a COTS engine, which means commercial off the shelf. So you just buy it from a retailer and then put it in your rocket. So here are some of the, on the screen are some of the specifications of the rocket that we did in 2019, which will end up being pretty similar to the one we do this year, obviously with some differences that I'll explain. So the rocket was 13 feet tall and ended up being around 70 pounds. Can you hear my cat? Is that why you say that? She's being loud. But anyways.
I couldn't hear your cat. But
Okay,
now that you mention it, maybe, but it was pretty good. It's fine.
She's upset because I put her out of the room. But anyways. So when we went in 2019, that was the size of our rocket and the weight. The engine that we designed, the hybrid one, is for around a 75-pound rocket. It's pretty hard to figure out what mass it'll be because you always end up adding more things to your rocket. But it'll probably be around the same height, but maybe a bit smaller because we're doing a smaller payload this year. But our engine will be taller, so it might even out a little bit. So in 2019, we actually intended to use the hybrid engine, which is pretty funny because here we are a year, 2 years later, still designing our hybrid engine. We were like, oh, we can totally do this in a year, and it ended up being way more complex than we thought. So now, in 2021, with much more knowledge, we plan to actually fly with the hybrid engine. The structures of a rocket that for this size are generally like glass fiber composites, like fiberglass for the actual body tube of the rocket, and the fins. And then we used aluminum brackets to hold on the fins onto the structure. And then in 2021, we will probably do about the same. We can't say for sure, it's up to the IREC team. The payload that we did in 2019, which is part of the competition, IREC requires an 8.8 pound payload. That's part of the requirement. So we made a deployable solar panel. I used deployment twice. Anyway, rover. And then this year, I think we're doing a CubeSat payload working with our advisor, who does CubeSat stuff in the department.
Hey, Avery,
And yeah.
do you mind defining payload for everyone if someone doesn't know?
Oh, okay. The payload is the electronics that you put on the rocket that don't have to do with the actual rocket flight, I guess. So the avionics have to do with measuring the flight data, and the payload is a separate piece. So we, like in 2019, did a rover, and this year we're doing a CubeSat. It's completely separate from the actual rocket function. Yeah, so then the avionics have more to do with rocket flight. So in 2019, we actually did roll control, altitude control, and then had various sensors on board to collect flight data. And the avionics for this year is to be determined. So here, oh, the heck. Oh no. Spoilers. Okay, so here is a sketch of our rocket in a software called OpenRocket that we use a lot. It helps you like input masses and components specifically to find the projected apogee, and then also your center of gravity and your center of pressure. Yes, we do love OpenRocket. So if you look on there, it's not a very clear image, but the little blue marking is the center of gravity, and the red circle is the center of pressure. So that's pretty helpful to know with your rocket design. So on this, you can see a few main things. The main structure is what's outlined. So if going from the top to the bottom, there's the nose cone, the upper airframe, the coupler, and the booster tube. And at the very bottom, the fins. The three things I listed in the middle, the upper airframe, coupler, and booster tube, are all just different sections of body tube that end up separating when you launch the rocket. That's why they have different names, but they're all just the fiberglass body tube. And then the stuff that goes inside of the rocket, you can see the parachutes and shock cord. The parachutes are, they have a little picture of a parachute in them in red, and then the shock cord is like the gray squiggly line. If you see in this one, we actually have 3 parachutes, and each parachute has their own shock cord attached to it. So the shock cord is just Kevlar like cord that it ties to the parachute, and then also ties to your rocket so that it doesn't fall to the ground very fast. And then the gray portion at the bottom, that is the engine. That is the commercial off-the-shelf engine that we ended up using at the competition in 2019. And then any other box that you see inside of the rocket is added mass. So you do that to kind of like add mass for your payload and electronics, I guess specifically, because that's what ends up with like adding extra weight. If you don't put those added masses in, then your rocket CG and CP that I mentioned before will be off in this. So you want to be able to put in as many masses as you know and you can predict, so that you can get a good estimate on your rocket apogee. Okay, so here is the CONOPS diagram from our 2019 IREC mission. So it looks pretty complicated. That's because our rocket separated into 3 pieces so that our rover could come out, but we'll start from the left here. So this was the original CONOPS diagram, was for having the hybrid engine in it. So that's why you can see on the left here, you have someone standing with the engine and someone standing with the rocket. So first off, what we would do is insert the engine into the rocket and put it on the launch rail. So then on the launch rail would be connected to the unmanned filling system, and then we'd all leave. That's why there's no people around it. You'd want to fill it when everyone is far away in case there were any issues. And then once that is done, you go to step 3, which is launch and powered flight phase. So that, when we say like powered flight phase, that's when there's actually thrust going. So it's going up and the thrust, the engine is still burning. Then when you go to step 4, the unpowered ballistic coast phase, that's when the rocket is still going up, but the engine is off now, so it's just still going up. Step 5 is apogee. At apogee, that is when your first separation point happens. So pretty much you have some like electronics on board your rocket that detect based on pressure when your rocket is at the highest point. And that'll set off a black powder charge that separates your rocket. And the separation occurs where the parachutes are, so then those come out and your rocket is under parachute. So first we have the nose cone blow off. That's why you see like a little nose cone and a red parachute. That completely separated from our rocket. And then the other two pieces separate or stay together. At Apogee, you typically have a smaller parachute that deploys called a drogue parachute. That's so that your rocket doesn't start coming down really fast. But if you were to deploy at a big parachute at Apogee, it would drift really far away. So you want to deploy a small parachute first, the rocket falls a lot further down, and then you deploy your big parachute. So that if you were to deploy the big parachute at the top, your rocket would likely drift miles away from where you launched it. Yeah, so those are all the things that have to do with descent. And then step 7 is rocket and payload recovery. So pretty much once your rocket lands, you use like I think in 2019 we ended up using a radio tracker, which was just basically we had a tracker on the rocket and then we used like an antenna thing and it beeped and we followed it until we found the rocket, which ended up being a few miles away, which was kind of intense, but very fun. Yeah, that's the rocket phase. Oh yeah, and then here are a bunch of fun photos of us at the actual IREC competition in 2019. It's definitely the most fun ISS trip I've ever been on. And the fact that we ended up doing really well in the competition, it was just really cool. In the upper left, you can see Andrew Larkey laying on the desert floor playing harmonica while we were waiting to walk back. Yeah, those are just some fun photos. Before I move on, does anyone have any questions in particular about any of the rocket stuff that I mentioned? Okay. Sounds good. Okay, doesn't look like there's any questions. Can move on.
Right before the break time card.
All right. Hey, everyone. I'm Avi. I was the testing lead for hybrid for 2019-2020. Testing was going to be one of our big goals for kind of the end of last year, but then, international pandemic hit, kind of a bummer, but, we dealt with it. So for this semester and for this project, testing is going to be one of the big goals. It's our primary method of determining the actual performance characteristics for the engine and verifying some of our design decisions. Also, it's the major opportunity for all of us to actually get hands-on experience with the engine aside from just building it. So I'll go into detail with these later on. I'll just give a brief overview now so you guys have kind of some context for what we're going to be doing with all this. Oh, thanks for the bacon compliment. I appreciate it. So our first test is just going to be high pressure nitrogen testing. It's going to be coming up pretty soon. It's a really simple test, and all it's meant to do is just characterize some of the parts of our feed system, mainly our control valve and our pressure sensors. After that, we'd be doing hydrostatic testing, which is required by IREC, and it's essentially where we just pump all of our pressure vessels full of high pressure water to make sure that it's pressure proof. After that would be cold flow, which is where we start characterizing the actual fluid flowing through the feed line and prove that the feed line can withstand all of that fluid flow. I said fluid flow a lot there, it sounded weird. Basically, this test is just going to involve us flowing all the oxidizer through the feed system without any combustion occurring and observing how the fluid behaves. All of that testing will then culminate with hot fire, which is where we place the engine on a test stand and fire it. And this allows us to characterize the thrust that's being produced by the engine and also make sure that we can combust without, blowing things up. Like I said, I'll talk about these more later, but now I just want to kind of get into some logistics for the testing because it's going to be a big thing this semester. So before, COVID times kicked in, we'd been talking to the people out at Purdue Zucrow Laboratories to design our testing campaign with the goal of actually performing all of our tests over there at Purdue with their expert guidance and kind of, observance. But given the current gathering and travel restrictions, this is looking less likely. But luckily, the folks over at Purdue are still very kindly willing to help consult on our testing plans and even sit in on some of our design reviews. But to keep some semblance of our actual schedule, we've been exploring doing tests here in Urbana at a retired jet engine test facility over at Willard Airport. ISS has done tests there with the subscale hybrid in the past, as we saw in that video earlier. And we have pretty good relationships with the airport officials there and the fire department, so that won't be too much of a problem. But based on some of the discussions we've had with the department in the past, they may not let us hot fire there. So hopefully we'll be able to get through the hydrostatic and cold flow test locally and then move on to hot fires at Purdue, pandemic conditions permitting.
So that's all that we had for the first day. We want to leave this time open for anyone. If you guys have any questions, we know this is a lot at once, and there's a lot of words and a lot of things you guys probably don't know. And like, don't feel worried if you're kind of confused. Like, everything will make sense in time, and we're here to help you learn things. So you guys, if you have any questions, please let us know. Like, this time is kind of just left for opening up questions. Because no one's got any questions.
I had a question for the people who attended. So like earlier when I asked people had like rocketry experience, there were several people who said yes. Is there anyone, like, are there freshmen who have rocketry experience? Did you guys come in with experience? Feel free to like unmute. I'm just curious.
I'm a freshman, and I did a camp at U of I, like a summer camp last summer, like the summer before this one, and like we just like we had like a small model rocket project, so like that was like my level of experience. So I just said like I had a little experience.
Yeah, that's cool. I also went to a U of I camp when I was in high school.
I'm a freshman also, and I took a online class from MIT about like intro to aerospace engineering, and there's like a little section about rocketry, and there was actually like he talked for like a couple minutes about the different types of engines and also hybrid rocket engines too. But yeah, that's why I said theoretically, because like I don't know, and I didn't do like physical rocketry stuff, but I studied it.
Yeah, that's definitely more than I did, so that's really cool.
The fact that like you have heard about a hybrid engine before coming to this or anything is like far above like what most of us has as background experience. So
yeah, definitely.
That's like kind of crazy. And yeah, if you guys have done KSP, like that's great. Like your knowledge of like mission profiles and orbital mechanics is way above what most people's is. So
I'm a freshman. Like, I mean, I watch videos and all that like online. I spend too much time like, I don't know, Everyday Astronaut, all those guys. But I also like over summers, especially this last summer, I built like a load of sugar rockets, like pretty big ones. And then me and my friend attempted to make a kerosene oxy rocket that kind of worked, but blew up twice.
So you said sugar rockets as well. That's really cool. But
I inadvertently brought a large amount of flammable powder. It's in my car right now, and I forgot.
Yeah, so the igniter that we're making for this rocket's actually going to be like a rocket candy based igniter. So it's pretty similar to the sugar rocket stuff. So could directly use that knowledge on this project.
You guys have any questions about like the beginning of the classes in the semester and stuff like that? That's another actually really great thing about like design projects in general, is that it's a really great place to meet older people who have experience about classes and can tell you like what to do and stuff. I've learned a lot of great advice from knowing older people in design projects, so hopefully we can share that along the line, down the line.
guess
yeah, continue.
Sorry, I was just gonna ask if any of you have been offered a co-op during your time at UIUC or an internship or anything like that, and how much you think that would affect your schooling.
I can answer the propulsion one first, the one in the chat. So there's if you guys are who asked this question? Yeah, Krish. I'd say the first class that deals with propulsion would probably be AE 312 if you're an aerospace major, which deals with
ME 410.
Yeah, ME 410 also.
It's the same class if you're a Mechie.
Yeah, that deals with compressible flows, which goes into supersonic flows, flows with heat addition, flows with friction, nozzles and how nozzles work, and a lot of the thermodynamics and fluid dynamics behind it, which isn't necessarily propulsion, but it's a lot of the science that's required for it. After that, there's AE 433, which is the aerospace propulsion course, which me, Avery, Raj, and Avi are all in right now, which goes over specifically rocket engines and air breathing engines. Specifically rocket engines and air breathing engines and design and analysis of those. And then after that, there's AE 434, am I right?
Yeah.
No. Yeah, which is rocket propulsion, that goes into a lot of the chemistry behind rocketry and a lot of like the really nitty-gritty details in it. There's also electric propulsion, which is taught by Professor Rovi, which is this whole other thing that we didn't really talk about, but is a very big part of propulsion research nowadays. And Professor Rovi's research group does a lot of really interesting things with that. So now about—
Actually, I'll even jump a bit further that the class, I don't know what you guys get, AE 311, it's ME 310. The first fluids class you take will be on incompressible flow, which basically just means it's not moving super fast and the density doesn't change. But we use a lot of equations from that class, just because the equations are much simpler and can be used for assumptions. And there's a lot of designs that use incompressible flow equations. So, I mean, really, there's stuff you can take. There's stuff we take from every single class that we get to apply in this project, which is really cool because, one, it makes you feel like what you're learning is useful, but it also makes you understand what you're learning a lot.
Who wants to talk about co-ops?
I think Larky is.
Yeah, I guess I probably should. I'm actually currently working on a co-op right now. I'm actually not taking classes, but it's cool because I get to do it remote. So I'm living on campus. So COVID has its ways of working, I guess. But yeah, I think I've mentioned this before, but I had no propulsion experience before joining the team 2 years ago, I guess. And at that point, I didn't really know what I wanted to do, but I knew I wanted to do aerospace stuff because rockets and aerospace is super cool. Oh, someone just asked what's a co-op. I think a co-op used to have like a specific meaning back in the day, but now a co-op is really just an internship, but in the fall or the spring or during a school semester. I don't know why we still use the term. It's just an internship. Anyway, so once I joined, sorry?
Co-op typically means you do multiple rotations. That's like the main difference.
Ah, that makes sense.
It's just multiple internships.
Okay. Yeah. Anyway, so once I joined the team and started doing a lot of propulsion, for me at least, and I think a lot of other people who are on this team found that propulsion is like really super cool, and a lot of us are trying to do this for a career in grad school or whatnot. But I've been able to apply to like internships, and I've done like interviews and a couple internships like directly related to my experience that I've done on this team over the past 2 years. So this team has been pretty valuable to me personally. But I think no matter like not just our team, but like even other ISS tech projects or even like a whole different RSO, like if you find something you're interested in and join a design project that focuses on that, like that's from what I've seen, that's by far the best way to gain experience for both like industry internships or research or grad school or stuff like that. It's the work you do is one, pretty fun, and it's also just pretty similar to kind of the sorts of things that industry works on. So kind of the way we go through the design process and kind of where we go through like design and testing, from like brainstorming, doing like large scale design reviews. They're all like meant to mimic the way things are done in industry or at NASA and stuff like that. So it's a great way to learn a lot pretty quickly. So yeah, this hybrid team has been pretty helpful for getting
Andrew,
yeah.
You're not going to tell them where you're working now?
Oh yeah, I'm actually working at NASA right now at the Marshall Space Flight Center in Huntsville. I'm actually working on injector designs right now for a research group that's trying to study some kind of advanced like future like lunar or moon or Mars missions. So pretty cool stuff. It's actually exactly what I'd want to work on for a career. So I got pretty lucky, but I was able to get this position like directly based off work I've done for this team. So yeah, you can take some cool experiences and apply them to a lot of other really cool things.
That's amazing. Thank you for sharing that. I appreciate it.
I'm not currently in a NASA internship, but I remember last year I had like a few interviews, and every interviewer was like thoroughly impressed with the hybrid stuff. Like I was interviewing with like, do you guys know Aerojet Rocketdyne? Yeah, so they do propulsion stuff, just a little bit, and I was talking to them about hybrid, and they were like very stoked on it. Like the engineers who I was talking to, they were just like pretty shocked that like students were working on that stuff. I mean, like obviously, I feel like a lot of colleges have it, but it's pretty cool to share with them. So
Yeah, so the hybrid engine team and IRIC clubs in general, if any of you guys are interested in working for big rocket companies, is like the best way to get into that kind of field. We have a lot of alumni who've gone on to work for some pretty awesome companies. Not only does it look good, sorry, I got to take some stuff off. You'll learn a lot of really, really great skills, which like are crucial when going into like the actual industry.
That is all great to hear. This is going to be awesome.
What do you guys think the odds are of actually being able to work on this stuff hands-on this semester?
So we can't ever really give 100% on anything, as one might expect. But the university has been working, especially the aero department has been working to create some spaces where students can work. We have the spaces we were previously using was in this really old building, mostly because of the construction at Talbot right now. But it was in the old building that didn't have good ventilation. They didn't want us working there. So they've been working on making some spaces for us to work. Right now, because of the 2-week semi kind of lockdown from that Chancellor Jones started, which is about to end actually. So we've been on like a temporary hold. But things, I guess the data is showing that things are looking up. So we're hoping to get back into things soon. But we're just based on like how much testing we do, we'll probably have like a fair amount of like hands-on work. And if you're here, we'll try to do a lot outside, which is definitely possible. Most of our testing is outside anyway, but we'll have some chances to definitely get hands-on work. So we'll be doing it safely, of course. But even if you're not on campus, or if you don't feel comfortable doing hands-on work, or if something happens and we just never get a chance to at all, there are tons and tons of things that we can do remote and do work online. There's lots of design and analysis work that we're doing, whether it's like CAD or just all sorts of like engine calculations, and also preparing for testing. There's a whole bunch of stuff. So if you want stuff to do, we'll have more than enough stuff to give out.
Also for online stuff, I'll be probably, like, we'll probably go into this in the next few days, like in the next few classes, but there's stuff called CFD, CEA, and FEA, which is computational fluid dynamics, chemical equilibrium analysis, and finite element analysis, which essentially means like you try and figure out if like a part works by doing simulations on it. Like if you're interested in that kind of stuff, we'll, like, a couple of us have background knowledge in this, and we can definitely teach you how to do that. And that's like a really good skill to have to show recruiters for internships and stuff like that.
Yeah, in the most shallow way possible, there are lots of opportunities to be able to put cool buzzwords on the resume. But you'll also learn a lot too, so you'll be able to talk about that stuff. It's all pretty fun and really exciting.
Also, we're decently fun for a project, like a technical
Yeah, I think
project.
we're a very fun team to at least
Rod,
humble
are you going to
ways.
describe us as decently fun? The most underwhelming way to say fun. You could just say we're fun. Like, decently fun.
Relatively fun.
Gotta keep expectations low.
That's how I describe everything.
No, we're actually pretty fun. We're also kind of cool, I think, because most ISS projects happen year to year. I know this year's a little weird because there's some projects that happened last year that they're trying to finish up now. But I think it's pretty cool that we already have like a lot of infrastructure. Like we're kind of like right in like the heart of our project and are getting things running pretty fast. So you can get involved in a lot of stuff really quickly, I think. So
You guys get to skip to some of the fun testing things, other than like us trying to find a way to test. So it's a fun time to join for sure.
Yeah.
As far as the testing goes, of the 4 areas, the high pressure, the hydrostatic, and the cold flow and the hot fire, have you guys actually done any of that yet? Or is that all to come throughout the next semester or two?
All to come through the next 2 semesters.
Yeah. We did one hydrostatic last year. We were testing our combustion chamber. It was a good opportunity, and I think we all learned a lot. It was basically, we figured out one of our major design flaws, and that's one of the big things that comes from testing, is just you realize things that seem like great ideas when you're designing are a little bit trickier to implement. So I'll speak a little bit more on that later when we talk about some of the more like actual specific design decisions, but testing is really fun and you get to learn a lot. So there's all 4 of those tests are going to be happening this semester and next. So yeah, a lot of opportunities.
We actually, there's like one test that we are like nearly like around the corner from doing. And the only reason we haven't done it is because a lot of our components are still in university buildings. We haven't really taken out yet. So as soon as we can get this 2-week restriction done, we're like really hoping to get some work going on some of those early tests.
Which does end this Wednesday.
Yeah. So hopefully we'll hear back from them. But most of the tests that we'll be doing in the fall semester are kind of more, or a little bit smaller scale, focused on kind of individual components. So we'll probably end up doing like the big hot fire next semester, which is where you get to integrate the whole thing, get combustion, cool flames, and stuff like that. So we still have some time to build up to a lot of really cool stuff. Also, is everybody on Slack or Discord? I know we sent an email out, but we usually do all of our communication on Slack or Discord. I'm not sure about the Discord because that's kind of a new thing we've added mostly during COVID, just because it's a great way to do like video calls. But so for most people, once you pay dues to ISS, someone from the ISS exec will add you to Slack. So if you're not on Slack, that's likely the reason why, I would think. But if not, we can also help very easily just put you on Slack. Yeah, so we've been using Discord a lot, honestly. Right now we're using both, but we're trying to make sure all the new people aren't being left out, or so we're trying to use email maybe through the end of this week, just as like a last minute heads up. But yeah, we'll be using Slack or Discord.
Yeah, so Dylan asked what is Slack, and Slack is a messaging software that's generally more guided toward industries and companies. So if you're working at a company, they're really big on using Slack. And a lot of the groups on campus like to use Slack. I really like it. I think it's a really clean software, and it's great for like organizing conversations and submitting files and stuff like that. Actually, quick note, if any of you guys have joined the Slack, make sure to take advantage of the thread feature in Slack, something that we like to harp on. But yeah, you can just search up Slack and download the software. And Andrew, you were saying the exec board reaches out after you fill out the membership form?
I'm not 100% sure, but I was pretty sure the way it works was that you pay your dues and then someone adds you to Slack. Is that not how it works?
I think that's the email list. So anyone can join the Slack. I think you can join it whenever.
That's the email list? Okay,
Yeah.
That's better. I feel less guilty about adding people to Slack then.
The information I've heard most recently is that the exec board would prefer you pay your dues before you join the Slack. I now realize that Dylan didn't ask, what is Slack? He asked, what is the Slack link? And I apologize, Dylan. My bad. Here, I can grab the link right now. Oh, you added someone I got yelled at, Justin?
I've added someone that I was expecting to get yelled at, but no one caught me.
Yeah.
So for people who haven't paid dues, does everyone at least know how to pay their dues?
That's good. Thank you, Avi. That's an important point to that conversation.
Because if that's not, no, that might be troubling. You just have to send either $10 or $15 to a Venmo account. Does anyone need that, or does everyone either has paid their dues or knows how to? Already done. Okay.
I'll send an email just reminding people. I was about to say I'll send a Slack message, but that's not, that wouldn't be useful. But yeah, there's a Venmo address that we use. And I think the dues are $10 if you just want like the fall semester, or $15 for the whole year. I would do the whole year. It's a better deal. Yes, also include your net ID so they know who you are.
I think I can pull up the link to the actual membership form right now. You guys give me a sec.
Yeah, so once you, in addition to being on the Slack and whatnot, there's also like a bi-weekly email newsletter, I think. It's either weekly or bi-weekly or something like that. But we send kind of all the updates, any important stuff about ISS, and also all like updates about the other tech projects and other cool things like apparel or maybe like social events, which I guess would happen on Zoom. ISS has a general meeting once a month, which has updates from kind of all the different facets of ISS, and they're usually pretty fun to go to. Yeah, and I think a lot of you guys have looked at other tech projects, but just as kind of a quick refresher, there are, I guess, 5 tech projects right now. We're technically our own tech project because for a year we were kind of by ourselves, and we're also like a very big project in itself. But like there's also the IREC tech project. There are a lot of people from IREC here as well. So we're like also technically a sub team of IREC because we're supplying them with their propulsion system, and they're supplying us with their rocket that we get to propel. A very symbiotic relationship. Yeah, so ISS is even beyond us. There's a lot of really interesting stuff going on. So Yes, Micro G, Justin, who's helped out a lot with our answering questions in the Zoom chat tonight. Justin's the tech lead for this year, but the last year's Micro G, which got a bit delayed because of COVID, I think they're doing like their testing like this week. So Micro G is a competition that stands for microgravity something. I guess it just stands for microgravity. But what they do is they actually, Justin, you're here. You should talk about it.
Yeah. So MicroG is Microgravity University, which is a program at Johnson Space Center. And last year's challenge, the tool is about to be tested in the Neutral Buoyancy Laboratory. I think that's coming up on Wednesday.
Yeah, so for those who don't know, the Neutral Buoyancy Laboratory is like a ginormous pool at Johnson Space Center, which is where all the astronauts hang out and work at. And it's used for simulating zero gravity. So all the astronauts do their training in there and pretend that they're in space. So it's super cool that all the teams that participate in this competition, usually they get to go there. This year they just mailed them all the tools, which, COVID. But it's really cool that they get to test their work on the closest thing to the ISS that you can realistically get to.
Megan asked if you can join multiple teams, and yes, you can. A lot of people do join multiple teams, or like run one team and be part of another one. As long as you're interested in it, willing to put the time in, you should.
Yeah, also especially for freshmen who are here, or anyone really, it doesn't matter. If you have the time to do different projects, it's also a really great way to kind of figure out what you like, because maybe if you just joined us, you'd realize that you don't like the project, or maybe you just hate us and you like propulsion, but you just hate hanging out with us, which is, whatever, that's fair. But if you get to do different projects, you get to really expand your horizons and see like what you like. When I was a freshman, I was busy doing a different RSO. So now I'm here. So if I wasn't doing multiple at that point, I wouldn't have figured out what it was that I enjoyed more. So yeah, so most people, like, obviously you don't want to do too many. You don't want to do so many that you don't have like the time to actually get the experience out of it. So a lot of people who first start end up doing 2. You don't have to do 2. You can do 1, you can do 2, you can do 3. Whatever works for you, but you just want to make sure you're getting a good experience from each project. Yeah, so over the next few sessions will be more content heavy. We'll get much more into the actual details of our propulsion system. We'll be here to ask questions at the end every single time, but our content will probably take more time than it did today. Oh, I always forget this, and thank you, Justin. So we also do a lot of educational outreach, which you should also get involved with. If you do our project, and even if you don't want to do our project, you can do only EdOut events. The EdOut team is really awesome. They do like lots and lots and lots of stuff, and help out a lot of people. And science communication stuff is a pretty cool and trendy thing right now. I've enjoyed the times I've gotten to help out there. They have a big Illinois Space Day online, Illinois Space Week online event coming up in October, which you can help out in and participate in. So that'll be super fun. Yeah, so ISS is, yeah.
You go first.
I was kind of just ending. So.
Okay. I was just going to say that EdOut does a lot of like visiting schools and trying to educate kids on what a career in aerospace or career in space is like, and like develop fun little projects with them. We just kind of get them interested in STEM stuff. A lot of like really fun stuff. So this meeting is officially over. We don't really have any more content. Probably going to, some of us are going